And what would you think? What would you think, where is the maximum amount of stress with this kind of displacement? Made up your mind? Hi guys, welcome to this video. Today I want to talk about the module 1 of the Altair Inspire course kit. So the module 1 is covering structural 3D. So basically that's a very important topic which every FEA guy must know. And so let's dive right into it. So basically, what will we cover today? So we have the structural 3D module. We will cover force creation. We will cover the material definition and supports creation, and also contouring. A little bit about load cases also maybe. And yeah, let's just see how it goes. So module 1 is here. You have also a solution which you can just check if you are stuck. Then you have like an instruction page, a PDF, or you have a PowerPoint to help you, and then you have a start here, which just gives you a little introduction into the module itself, so you can see, all right, this is what we'll be doing. And so there's also a video with it with text annotations, but I will just go over it and just tell you what I think. And maybe there are some few nuggets here and there which I can contribute to this module. All right, so let's start. First things first, you have a module y bracket dot x underscore b. Yeah, so this is a geometric format, and this will just load in the geometry. So you see, I just drag that into Altair Inspire, and boom, I have it here. So basically, I can just review the part a little bit and see what it's about. And basically, what it wants me now to do from the exercise is do a support here and do a force and here and here. So those two holes here will be, there will be a force applied to it, and that's the load case. Okay, so far so good. So we are home here at the structure tab. Then we have the constraints, right? So not this one, but this one. This is the constraint symbol. And basically I just have to select it here, but be careful. You see that it highlights the line or surface. We want to have the cylinder surface, so be sure that it is highlighted like this before you click. If you click like here and have it wrong, then you just click escape, select it, and hit the delete key, and you're done. Okay, let's get that going. So like this, select it, right click, and swipe to the left to complete the action. And now you see in the properties window what you have here. So if you select this one here, you can see here the properties, right? So we will see that all the degrees of freedom are constrained. That's what the tutorial calls DOF 1 to 6, and here it's TXYZ and RXYZ. So those are the kind of constraints you have. Because it's a cylinder, it just allows you to free the translation in Z and the rotation in Z, and you can see by the green arrows what that means. But in this case, we want to constrain all the degrees of freedom to have a really fixed part here. Just imagine it being glued there. It cannot rotate, it cannot move, it cannot do anything. All right, now forces. Force icon is also here, so you can select that. And the same thing here again, you want to select it like this, so that the cylinder is selected. Not like this, not like this, but like this. Okay, now I think the tutorial says it should be both in positive X direction, so let's get that over. And then let's do some reasonable force. I think it's 1500 in the solution model, and do the same thing here again. And also should point in the same direction. You can see both forces point in the same direction. So that's that. Now, load cases, pretty big topic, and also very important that you know that. So you can see this little icon here. This icon opens up like a page, and there you can see your load cases. For example, I could say I want another load case where I have the same support, but I just want force 1 to be acting, and then maybe another load case where same support but just force 2 to be acting. And so you can see you can define all the forces you have and then define your load steps or load cases, right? So that would be how you do this. Right, and you can also remove them. So let's just do 2. That's I think it's enough to show how it's done. Now, also very important is that you have a material definition. So be sure to check that you have a material assigned and do that on purpose. there's no bigger mistake than thinking you have a steel part but modeling it as a plastic part. It will be way off, and that's very important. So here we go with a steel, and that's, I think, fine for the tutorial, but you see, check that, right? Every part should have the correct material assigned. Now, another thing also to take into account is to be sure that you set the solver to what you think you would want it. I think the tutorial mentions that you would have to use the OptiStruct solver and define also mesh size, which is fine, but there's also the option to use SimSolid, which is a meshless solver, and for those easy kind of simulations, it's definitely a good thing to start with, right? So can get you results far quicker than OptiStruct, because OptiStruct does have to do the meshing and is more computationally expensive. So basically SimSolid is the faster way, but be sure to check it also with a mesh-based approach. Okay, but this is a whole nother topic, not something I would want to go into in this video. Now, SimSolid is selected, should be fine, I would say for now. Let's just run the analysis. For running the analysis, you just click here the play button for the analysis section. Then you would give it a name, and you can do some settings here. This will be different for OptiStruct because there you have to choose the mesh size, but here we don't have to, and we can just quickly check this, but that's not too much to worry about. We don't have modes or buckling, we don't have gravity, and the load cases, you can also select the load cases again, load case 1 or 2. In this case I will just run 2 to just show you how it's done. Alright, let's click on run, and you see this will be instant, right? Very, very quick. So for SimSolid, it's not mentioned in the module, but I will mention it anyway. There's this crazy good feature to just check the reaction forces. And I would urge you to do this. Wait a second. Like so. It doesn't work. Oh, okay. Let me see. Here we go. So basically, this is, I had to click on the green flag to load in the results, and then you have this reaction force check. You can now press on the bearing here and on the constraint, and you can just check that what you gave into is also what you're getting out. And I think this would be the load case, I don't know, should be load case 2, I think, because I'm getting 1500 newtons. That should be the equivalent of one force. Yeah, this is load case 2. I think there should also be load case 1, but I think, wait a second, I will have to load case 1, see if I can fetch the load case. Okay, so here I can switch it. So load case 1 should have, in this case, 3000 newtons, right? So that's also very important check that you do this. You have a force you apply to the model, and then you have constraints, and the forces you apply to the model and the forces being at the constraint should match. That's when you know you don't lose any force, right? It's just a basic model check. Okay, so let's go back to the result and let's just do the load case 1 with both forces, right? Yeah. So load case 1 has both forces. Yeah. So, okay, you can just check the displacement. By the way, I think for me it's a default case for a long time since I installed it, but if it's showing on a different color scale, you can go here on visualization. No, wait a second. Run options? Yeah, run options, and then you can see how the colors are. And for example, I think the normal one is like single color, but I hate it to the core to have that as a single color. So I will do it all with rainbows. And that's pretty standard in industry, I would say, to do this color plot. Okay, so blue means nothing, red means much, and you can see the scale here. So we have 0.3 millimeters or so on your maximum displacement. You can also animate it. You have this play button here, which animates like the deformation. That's also good to check if the model does that what you think it should do, right? So just check it. And what would you think? What would you think, where is the maximum amount of stress with this kind of displacement? Made up your mind? Let's check it. So going here to von Mises stress, you will see that it's here in this corner. You can also show it with the min-max symbol here, so you can see it here where it exactly is. And you could also do tension, compression, and a lot of more stuff than the module goes over. But I think the most important things to take with or from this module is how to set up constraints and forces to make the differentiation between SimSolid and OptiStruct. I can also quickly show you how it would be done in OptiStruct, and be sure to check that, because, for example, let's just say I trust this result. This result says 142 megapascals as stress. Now let's see if I do just simple file preferences. I will check and switch the solver to OptiStruct and just run the analysis again, and I will just go with the default mesh size it would just say I should use, right? So if I just click on run here, and it will take a little bit longer than SimSolid, but not considerably, I think, because it's a rather big mesh size. And just pay attention to the number 142 megapascals would be the expected value, more or less. And let's just see what this will come up with. So I will pause the video, and we're back. So it's now completed. Resultant force check is a little bit more complicated in OptiStruct, but it's definitely possible, but I will not go over it. If you want to see the mesh, you have to go here and just click this button. And that's where you can see also a little bit of the discrepancy. Hey, Manu from the future here. So I went back and made a little bit more of an analysis to see where this discrepancy is coming from. So what you're seeing here in Hyperview or Hypermesh is the model which Inspire will create, and not on the top left. This is with the default values, and you will see this result on the right here. So as you can see, you have a pretty big hotspot directly here at the hole, which comes from the fact that if you look into the model how this is done, here is an RBE3 element, right? And this RBE3 element says, okay, I'm defining my constraint here, and those nodes here, they cannot move however this constraint is defined. So basically you are locking those nodes here that they cannot move. And then if there is a movement of those nodes, this element is getting squeezed. And so this will see a lot of stress. And because of the mesh size, you can see on the right, this is more or less in the hotspot zone of the SimSolid solution, which is why it's a bit confusing. But those should be separated. So to separate that, what you can do is to decrease the mesh size, and you can see the effect on the two lower screens. So lower left shows this, I think, is 8 to 10 millimeters. Here is 5 millimeters, and here is 2 millimeters. And on the 2 millimeters, I think you can see it the most clearly. So you can see here the hotspot still there, also with the high 220 megapascals or so. Also here you have to take into account this is a sharp edge, no roundings, so this also is a singularity here, which will be generated by the mesh-based solution. But if you just see roughly in this area, right, roughly, you're getting with the color scale a lot lower. And if you compare that back to SimSolid, this is a lot closer to this solution, which is found by SimSolid. Basically, just to go over once more, what you can take from this module is how to set up the constraints, the forces, how to do your run options with SimSolid or OptiStruct, and based on which solver you would want with OptiStruct, how to also change the mesh size. That was with the run options. You saw the contouring with the results. You can see and animate the results with the play button here. You can also have something like a probe, where you can just see how much is the stress at a particular location. And another thing, you can also just push the slider up and down and just see which areas really have the high stress. So there's a lot of visualization techniques how to do this. And load cases, you can switch them here, also do envelope plots here, and stuff like that. So yeah, so you see, there's a lot of things to do and explore. So I would urge you or recommend to you that you check it out for yourself. Go have some fun with the model, just see how it works, and you can always check the solution if you are stuck, or rewatch the video how I did it here, and you should be able to get to a converged solution easily. And then do some research, ask maybe also a large language model, and refine your understanding of solid mechanics. Maybe also do a little bit of a hand calculation to just see and check your results, and just dive into this wonderful topic you have at hand here. Alright, that's all for today for this video. I hope you have a good day and a good time with the module 1 of the Inspire course kit, and I'll see you around. If you have any questions, comments, requests, or criticism, please leave them down below. I'm happy to read them and do my best to help you form a better understanding in this topic. Thanks guys, and bye.